In this video, we define a new parameter called the independence number of a graph that we'll see later on as well. And we establish a connection between independence number, connectivity of a graph, and Hamiltonicity of the graph. So that is, we'll see if a relationship holds between the independence number of a graph and the connectivity of a graph, then the graph will be Hamiltonian. So another sufficient condition to be Hamiltonian. So first off, we need to define independence number of a graph. So a set of vertices in G is independent if no two vertices in U are adjacent. So that is, an independent set of vertices is one that is pairwise non-adjacent. Then the maximum number of vertices in any independent set in the graph is called the vertex independence number, or just independence number of G. And we denote this as alpha of G. So a couple examples here. If we look at, say, a complete graph, let's take K4 for example. So here's K4. Well, any two vertices I pick are adjacent to each other, and so the only independent sets are just the singletons, just single element sets of vertices. And so the independence number of K4 is equal to 1. That's the maximum size of any independent set of vertices, because any two vertices are adjacent. And in fact, in general, the independence number of Kn is equal to 1 for n greater than or equal to 1. That's for all complete graphs. This is the case. And we can actually say more about this, that the independence number of G is equal to 1 if and only if G is Kn for some n. Right, if the maximum size of an independent set is just 1, that means that any two vertices must be adjacent, and therefore the graph is complete. And so that is a useful fact that we'll use later on. Some other things we can look at are, say, cycles. So let's maybe take the cycle of order 6, just to illustrate the idea of independent sets. Here's C6. And C6, so what's an independent set here? Well, maybe I can take this vertex, but then I can't take those two because they're adjacent to that one. And so I could take this one, and I could take this one. So this is n, the independence number of C6 is equal to 3. Why don't we take, how about C5? Let's look at C5. What does it look like if I have an odd number of vertices? So I could take this one. I couldn't take those two adjacent to it, but I could take this one, and then I can't take those two adjacent to it. And so it looks like the maximum size of an independent set here is 2. So alpha of C5 is equal to 2. And in general, this will continue. If I have an even ordered cycle, I can take every other vertex for an independent set. And so I'll get n over 2. So alpha of Cn equals n over 2 if n is even. And alpha of Cn will be equal to, n minus 1 over 2 if n is odd. And so in general, alpha of Cn is equal to n over 2, the floor of n over 2. So that's, I want to look at any other graph. Oh, how about a complete bipartite graph? So complete bipartite graph, let's just do it in general. So if I have the bipartite graph KRS, where say R is less than or equal to S, R vertices up here, S vertices here, and I have all these vertices in between, or all these edges in between. So I have the complete bipartite graph. Then if I take one of the partite sets, that'll be independent. So each of these, I'll just circle one. This would be an independent set of vertices because there's no edges between them. And then also if I take S, that would also be an independent set of vertices. So not together, but just on their own, each of these sets is independent. And so the independence number of KRS, where R is less than or equal to S, would be equal to the max of R and S. So in this case, S would be the maximum size of an independent set. I can't do any better than that because if I took these independent vertices and added any other vertex to this, necessarily there would be some pair of adjacent vertices in that set. So this is the idea of an independence number of a graph. It's the most number of vertices that we can put in a set such that no two of them will be adjacent to each other. So pairwise non-adjacent. This is sort of the opposite of a complete subgraph, right? It's a complete empty graph. Or sorry, it's an empty subgraph of a graph. That is, if we take an independent set of vertices and induce a subgraph on them, we'll end up with an empty graph. Okay, so I'm going to erase this because I think I went a little bit outside my borders here for this next proof. So I want to remind you of a couple concepts and key theorems and corollaries from connectivity. So remember the connectivity of a graph. Sorry, my computer's lagging a little bit here. Connectivity of G, remember the symbol we use for that is kappa, is the smallest cardinality of a vertex cut of the graph. And we had a couple corollaries and theorems that went with this that we'll find useful for proving this theorem below. So corollary 4.13, if G is k-connected, so the removal of any fewer than k vertices will not disconnect the graph, and we choose these t vertices, u, v1, v2, up through vt, those are distinct vertices of G, then we can find a uvi path for each I between 1 and t. All right, so I pick these. We didn't really talk about this one in class, so I'll illustrate it here. So here's my vertex u. I have v1, I have vt, v2, v3, up through vt. Then if G is at least k connected, so this is for t. I don't think I have the entire theorem here. Sorry, 1 second. I want to say a little bit more. I need an extra bit to my hypothesis here. How does t relate to k? Oh, yeah, so this is for, yeah, as I thought, for t less than or equal to k. So for any t less than or equal to k vertices of G, then what I can do is I can find independent paths from u to each one of those vertices. So they'll just have u in common. I can find this. Also, theorem 4.15, if G is k connected, then every k vertices of G lie on a common cycle of G. That'll be useful. And then finally, we're going to use these results to prove this theorem. So if G is a graph of order at least 3, if the vertex connectivity is at least the the vertex independence number of the graph, then G is Hamiltonian. So if connectivity is more than the independence number, we are guaranteed that G is Hamiltonian. Okay, so this is a long one, so I'm not gonna prove every last little bit of it, but I'm gonna show you a sketch of it, and I'll kind of talk through. I'll mention the arguments, but I'm not going to write them all down. All right. So if the independence number is equal to 1, then G is complete. And therefore Hamiltonian. And so we would be done in this case. So we may assume that the independence number of G is at least 2. And so our assumption is that the connectivity is more than the independence number. So we have that the connectivity is also at least 2. By this theorem up here, theorem 4.15, that means that it's 2 connected, and so it has to contain a cycle. Hence, G contains a cycle. A cycle C. Why did this? A cycle C. So let C contain, let me just say it contains a cycle. The graph has at least one cycle in it. Let C be a cycle of longest length. We show C is a Hamiltonian cycle. That's what we want to show here, is that a cycle of longest length contains all the vertices. We also know that C, the length of C is at least K by theorem 4.15. Any K vertices lie on a common cycle. So since this graph is K connected, we can say the length of C is at least K. So by theorem 4.15, the length of C is at least K. So C has at least K vertices on it. And we want to show that it's a Hamiltonian cycle. So suppose C is not a Hamiltonian cycle. Then there exists some vertex that is not on the cycle. So here's where things start to get a little bit messy, and I'm just going to draw a picture to help us out. So here's our cycle, C. Now usually I'd use this for like a block, a bunch of vertices inside of here, so I'm going to draw vertices on the outside of it. We have at least K vertices on this cycle, but generally we have a lot. And then I have some vertex W down here, let's say, that is not on the cycle. Okay, so by corollary 4.13, since G is K connected, I can choose W and then K other vertices on the cycle and find these paths from W to these other to K other vertices on the cycle. And I can do this in a way, right, I can choose shortest paths from W to the cycle, and so I can say that these paths from W to the cycle, these K paths, will contain only one vertex of the cycle and will not intersect each other. So pairwise disjoint paths, except for W, so internally disjoint paths. So, okay, so I have these paths going from W up to my cycle. I have K of them. I can't say every single vertex is on here, but I certainly have K of them up here. And I'm going to call these paths, so these are paths, not just edges, so I'll put some vertices on here. There's at least one. Well, there could be no vertices on each of these paths. It could just be an edge. But I'll just draw some vertices, and just keep in mind there might not be any. There could be a lot. We want to keep it general. Some number of vertices on each path. And I'm going to call each one of these each one of these vertices V sub I. So V sub 1, V sub 2, V sub 3, V sub 4, V sub 5, let's say. And again, there could be more. In general, I want K total paths. So maybe I'll call this one V sub K. And maybe there's some more here too. Let's call that V sub K. And then what I'm going to do, I'm going to use this independence number bit. So I've used the connectivity a lot to get the cycle and all of these paths leading from W to the cycle. I'd like to produce a longer cycle and get a contradiction. So what I'm going to do is I'm going to find a set of vertices that are independent. So I want to, so let U sub I be the vertex immediately after V sub I on C. So that is this V2 here would actually be U sub 2 as well. So that's okay. We have double labels for this. That's fine. U sub 2 is equal to V sub 2. And then there would be this vertex immediately after V sub 2. This would be U sub 3. Or sorry, U sub 2. Sorry, this one would not be U sub 2. This would be U sub 1. It's the one immediately after V sub 1 on the cycle. And then over here, this is the one immediately after V sub 2 on the cycle. So this would be U sub 2. Over here, I'd have U sub 3. I'd have this vertex over here. That would be U sub 4 immediately after V sub 4. And so on. So I'd have UK here. And then I'm going to collect all of these. So the first thing I want you to notice is that if W U sub I is an edge, I keep drawing a slash through it. If W U sub I is an edge of the graph, then what I can do is I can replace V sub 1 U sub I, or V sub I U sub I. I could replace this edge with the path from V sub 1 down to W, and then take the edge from U sub I to W. So if I suppose U sub I and W are adjacent, then I could take that edge and produce a longer cycle. So that can't happen. Sorry, let me erase this edge and redraw the path. And that would be a contradiction, right? We're assuming this is the longest cycle. So W U sub I, now I get to do a slash through it, is not an edge for each I. So now I have this collection of vertices. I'm going to do W, U sub 1, U sub 2, up through U sub K. I have all these vertices. These are K plus 1 vertices of G. And I know that the independence number of G is less than the independence number is less than or equal to this K. K plus 1 vertices. But the independence number of G is at most K, right? That's the connectivity of the graph. Hence, this can't be an independent set. There is some edge between vertices in the set. Okay, so there's some pair of vertices up here that are adjacent, but I already showed that W U sub I is not an edge for each I. So what this means is that some pair in the U sub i's have to be adjacent. So that is U sub R, U sub S is an edge for some 1 less than or equal to R, less than S, less than or equal to K. So 2 of these U sub i's must be adjacent. Let's suppose, why don't we suppose U sub R, let's suppose this is U sub 4, U sub R, and then over here maybe V sub K, U sub K is U sub S, is this next one. So what we do then, how do we obtain a longer cycle here? Or what can I conclude? Yeah, that those are adjacent, right? So U sub R and U sub S are adjacent. So I have to have an edge connecting these 2 vertices. So how do I produce a longer cycle here? This took me a little bit to remember how to find the longer cycle. What I'm going to do, I want to use this path from V sub K to W, this path from V sub R, so V sub 4 to W, and I want to use this edge between them. Okay, so I'm going to start here at v sub 1. Okay, so I travel along the cycle, I'm going along the cycle, doing everything normally, and then I get to v sub 4. Yeah, here's where I want to be very careful. So I want to get a longer cycle. Got it. Okay, so I get to v sub 4, and now I'm going to take this path from v sub 4 down to w. All right, I get to w, and now I'm going to take the path from w to v sub k. And now I'm going to go backwards along the cycle, back to u sub 4, and then take that edge that I just worked to show that it existed from u sub 4 to u sub s, and now I complete the rest of the cycle. So I've hit every vertex in the cycle, and I've necessarily now included an extra vertex in it, producing a longer cycle. So I guess I just showed you up there. I'll just say we can now, this is why I called it a proof sketch and not a proof. We can now find a longer cycle, which is a contradiction. And so it must have been the case that this cycle contained every vertex. And that concludes the proof. Okay, that's it for this one. Yeah, read through this in the book. You might have to come back to this video and watch this little segment again for how this works. If you have any questions, let me know. I'll see you later.